Fine, let us start then. So we were looking at and what we want to look at is ultimately the cross section. And we started with this is our starting point. This is what I had called AM. So AM dot, so the dt became d4x over here on the right hand side. Okay, and we had phi f star, which is a function of the 4 vector x, h int or v times phi I again of 4 vector x. Okay, and then we use the Klein-Gordon equation. So we are looking now at
yeah. Video quality is not very fine.
Video quality is not okay.
Can you write in a bigger font?
No, one second. Actually, I just asked.
Can video quality be increased?
Yeah, that's why I just asked Kripa to leave. I'll ask him to come back. 1 second.
Because I'm trying to make out very quickly.
1 second. I'm looking for a phone in this room to call Kripa. 1 second. அது அந்த வீடியோ குவாலிட்டி அவருக்கு இது தெரியலையா கொஞ்சம் மேனஸ். தேங்க்யூ. Okay, I will write bigger and until he comes, he is in the other building, so I think he zoomed out too much, right? ஓ எங்கே இருந்தீங்க? பக்கத்துலேயே இருந்தீங்களா? ஓ சரி கொஞ்சம் ரொம்ப ஜூம் அவுட் ஆயிருக்குது, அவருக்கு தெரியலையா? இன்னும் கொஞ்சம் ஜூம் இன் பண்ணுறீங்களா? Tell me when it looks okay, the size. Is it better?
Yes, sir.
Or should it be even closer?
Yeah, it's better.
It's fine? Okay, fine. கொஞ்சம் திருப்புறீங்களா? கொஞ்சம் திருப்பணும் ஏன்னா ஒரே நிமிஷம். ஆமாம் இல்லை ரொம்ப கம்மியாயிடுது. சாரி, 1 செகண்ட். இது இவ்வளோதான் தெரியுது, என்னாச்சுன்னு தெரியல. சரி அதான் yeah, that's what he's trying to adjust that. Normally he
on the other side.
அப்போ இல்லை ரொம்ப இல்லைங்க ரொம்ப இதாகிடுது இப்போ. நோ இன்னும் கொஞ்சம் இன்னும் நிறையா போடணுங்க. ஆக்சுவலி கொஞ்சம் ஜூம் அவுட் பண்ணுங்க. போடும். இது ஓகே. இது ஓகே. இது வரைதான் ஓகே. இல்லை அங்கே அது வரை வரல, இது இங்கேருந்து தான். அவ்வளோதான். சரி, ஓகே ஃபைன். நான் அட்ஜஸ்ட் பண்ணிக்கிறேன், நான் பார்த்துக்கிறேன். பட் த லெட்டரிங் இஸ் நவ் கிளியர், ரைட்? Yeah, for some reason it's a very small part of the board, but I'll manage in that, okay? But you can see this, right? Lettering is clear?
Yes, sir.
Okay, fine. Yeah, I'm not going to write this again, but I have a different part of the board, so I'm going to write here, okay. So this is
Ravi is not in yet.
Oh. So what you do, Krishna, just click on his name No, just Krishna, just click on his name. On the right hand side it will say more. Make him the host. Okay, he is now the host. So Ravi Shankar, you are now the host. Now you ask yourself to enter and you allow yourself in. Okay.
Okay.
Yeah, just, and if you have a difficulty, just let us know. Okay. So what we had started was a spinless electron or some charged particle. And we started by writing the Klein-Gordon equation. And then we identified a J mu, which was rho. I mean, there should be a C rho, but we know that H cross equals C equals 1, and that was and I won't guarantee the overall sign. And with this, and if you put mu equal to 0, you get rho, and you found that that was normalized to 2E states per unit volume or per volume V. Okay, and so this was simply the number operator and that confusion that we had. So okay, so if the Q is the charge of the object, then I will define an electromagnetic current J mu, which is Q times J mu. So this is the number current, and therefore if I multiply it by the charge, I will actually get the electromagnetic current, which will include the charge. Okay, so that was one question that we had last time. So what we did was we replaced over here P mu by P mu plus E A mu, and that's how we turned on the interaction term. And we identified inside this, by we put it back in the box equation, we identified inside this that H mu was the H int or the V was minus I E, I don't remember what that was overall. So we have Q now, Q d mu E mu plus d mu. So we put that back over here, H int is V. Okay, and we got an expression for TFI. So what did we do? The first term, d mu acts on both a mu and phi I. So we did an integration by parts, and here the d mu acts only on phi I. So we got two terms where we had d mu acting on phi star because we did an integration by parts, and the other which had d mu acting on phi, and that gave you a negative sign with respect to the two terms, and we identified that as being an object which is similar to this current J mu, but what we call J mu Fi, because it had d mu phi f star phi I minus phi f star d mu phi I. Is this what we got? So everyone remembers that. So we got TFI as E or minus E.
You are integrating by part with respect to what?
Here, let me write the terms then instead of saying so many words. Let's start by writing TFI. So we have not yet reached here. TFI is minus I d4x phi f star. Now I am substituting d mu a mu. There is a q outside. There may be a further I. Please look at the notes. Now I write the first term as, so I think that I is not there. So that I am not guaranteeing. So I have now this first term is this. So the first term, let me write it down, phi f star d mu a mu of phi I t Fi first term, that is equal to phi f star A mu phi I
Ma'am,
at minus, yeah?
I think there should be negative sign in front of Q, second line.
Yeah, I'm sure. As I said, I'm not going to guarantee the signs. You have to look at your earlier notes and then write it down. So, see, I can get all the signs right by holding up my notebook in front of me, but it just takes me more time. So, I just forget it and I will leave. So, I just want to show you this. So, what I have done is that I have taken the surface term. So, this is the surface term. So, this will be at infinity, right? Because I can in principle make my a volume of integration as large as possible, and I know that all these fields die out at infinity, okay. So, I do not have any contribution from the surface term, and so this term just becomes minus of the d mu term acting on phi f star. So, that is what I am going to write. So, now I am going to write t fi full will be minus of this plus of the second term. Is it clear?
And there will be a fourth surface term, and in a 4-dimensional, how it defines surface if
It's a 4-dimensional surface, right? Surface is a surface, whether it's 2-dimensional, 3-dimensional, 4-dimensional, it doesn't matter, right?
Generalization of Gauss divergence.
Yes, it is the Gauss divergence theorem in 4 dimensions, that's all. Also, see, by definition, so you don't have this interaction. What is it you are saying? These terms, the A mu term is localized. So, you remember that whole diagram, right? So, at t minus time t minus infinity, these are free states. The agent is turned on around t of the order of t naught of the order of 0, and then I am doing the detection at t going to plus infinity, right. So, all these terms, especially this interaction term, all these are 0 on the surface, nothing is there at infinity. Even if you look at the remaining fields, even if you look at the phi i's and phi f's, they are free states, but then they are all well behaved, right. So, they all also die out. Space contribution of that will be 0 at infinity, right. So, we are always assuming that these terms die out at infinity, because you want the wave function to be normalizable. So, they all die out at infinity. So, even if the time part, they are there at t equal to minus infinity, in the space part that will be 0, so the whole term will be 0. So, all the surface terms are 0, okay. So, this was what I identified as up to a sign, we do not know what the sign is, as j mu fi times a, okay, and there was a q, so we will put the q over here. So, we will put the q over here. So, either you put back the q inside here and call this j mu electromagnetic, or we keep the q outside and call this a number j mu, does not matter. But this is the j, this is what I call the j dot a interaction, which is the quantity that you are going to see again and again, independent of the nature of the interaction. So, whether it is now electromagnetic or later on weak or strong, we will find such a j dot a interaction appearing again and again. Is it okay? So, now what did we do with this? We stopped at this point and said, now let us take a physical example, and we took the physical example of electron muon. Just one moment. Kripa சரியா தான் இருக்குது நினைக்கிறேன், நீங்க கழுமல, ஆமா, thank you. So, we took this example which we called A, B goes to C, D, and then we interpreted this TFI as, maybe you can say, J of the AC current interacting with the A coming from the BD current. So this is the JAC, this is the JBD. So either this A is coming from the BD current or the A is coming from the AC current, and we got a symmetric answer by writing that the A which arises from, let us say, BD satisfies box A is equal to J, and since we know, yeah,
Ma'am, could it be this process can be defined like this? Like, if I say I have two fields, one electromagnetic field and one scalar field, and the excitation of electromagnetic fields are photons, and excitation of your scalar field, say it is a scalar meson, right? And we are interacting meson with photon. Could it be defined like this? Can we define this process like this?
no. All we are saying is that these are all elementary particles. A, B, C, D are elementary particles. Okay. So what we are saying is that as the A particle moves along, it emits a photon, okay, or as the B particle moves along, it emits a photon, and either B absorbs it or A absorbs it and converts to the particle C. So let us take a specific example which I have taken here. So as maybe I will even exaggerate the diagram so that you can see it better.
Ma'am, there is no incoming photon, right?
There is no incoming photon, that is why. So this is at this vertex, okay, at this vertex B emits a photon, okay, and changes its momentum from PB to PD. It's the same particle, it's still a muon going to a muon, okay, still the same particle, and at some other later time, so this is the time axis, so at some later time, so delta t later, this A absorbs this photon and goes from a momentum Pa to a momentum Pc. So the momentum q of this photon, oh god, now I realize, okay, we'll be careful. I removed E because E was the electron, but now I realize q is this momentum, but okay, let it be. This is a small q. So q you can see is Pb minus Pd, right? And so that absorbs, or that is absorbed by the A over here, and so Pc is exactly Pa plus Q. So you can see that we have set it up, and that's how the energy momentum conservation function comes out of this expression, right? So all we are saying is that the way to look at it is that this A is interacting with some photon, and the origin of that photon is from the current Bd, and that is what I am writing over here in this expression. Okay?
In this procedure, when we are learning quantum field theory, so if we use elementary particle as our fundamental things,
Yes.
then what is the difference between doing here and with quantum scattering process in quantum mechanics? Means, ma'am, I don't able to understand why this is different.
Okay, you people have learned statistical mechanics, right? Quantum stat mech you have learned.
Yeah.
Yeah. So this is the difference between canonical and grand canonical ensemble. See, what we are saying here is a simple example. Electron goes to electron and only its momentum changes. But we know that, maybe, okay, fine. Since this question was asked, before I solve this equation, let me explain, since this is coming up again and again. So we know that we can have, for example, electron positron annihilates to produce gamma, right? We have seen also, for example, neutron decay, we discussed it, right? Now what do you have in the canonical ensemble? You have number conservation, right, which you don't have in the grand canonical ensemble. Here, what is the wave function of the neutron? at some time t equal to, oh god, I rubbed it out, at some time t equal to t naught, when this interaction takes place, the neutron has simply disappeared. It no longer satisfies in fact it's equal to 0 because that particle has disappeared, right? So in quantum mechanics you don't have the option for such a thing. In quantum mechanics you always demand this, and you generalize that by asking for a continuity equation with d mu j mu equal to 0, right? Now here what happens is that you think exactly the analog, and you will see that you can write this exactly in the grand canonical ensemble and write a quantum field theory based on that. You will find that this is allowed because your total number is now changing, okay? And you can write everything in terms of statmech quantities, okay? There is a way of writing your entire, you won't do it in the first semester, but if you continue with field theory in the second semester, you will see, or maybe I don't know, Ravi may do it, what is called functional approach to quantum field theory, which is essentially looking at it from the statistical point of view, okay? Is it clear?
Yes, sir.
So sometimes in the olden days, yeah?
And do you mean statistical field theory?
Statistical field theory is slightly different, okay? It's not the same. This is writing quantum field theory in, so it's called a functional approach. Statistical field theory is yet another thing which, okay, they're all nice things, okay? So sometimes you would have seen this word, it was a very common word, it's no longer used. It's called second quantization. I will tell you in some, like very hand waving way what we mean by it. We look at Dirac equation, right? We will in fact look at it next week again. When we look at Dirac equation, what did Dirac say? He got an infinite number of particles, states, and so his whole theory would have collapsed, right? What did he do? He said that all the negative energy states are filled. And when you remove one of the negative energy states, one of the positive energy electrons can fall into that state, and that's the meaning of your electron hole annihilating to give you energy, okay? So he identified those objects as holes, okay, and then we later associate those holes with positrons. I hope all of you have done Dirac equation and know this interpretation.
Yes, ma'am.
Yeah, especially among the new students.
Yes, ma'am, we have done.
Okay, very good. Yeah, very good. Okay, so this whole interpretation, which in fact took Dirac 3 years to come up with. I mean, he took such a short time to write down his equation and his solution. He took 3 years to figure out what that solution meant, because he had one wave equation and 4 solutions. And it was such a remarkable, I can't even imagine today how he even thought of it, thought of the fact that antiparticles can exist. And only after he wrote down his equation, people went and looked for antiparticles in the lab and found them. And for him to have been so sure that that is the interpretation is really remarkable, okay. So, but if whatever you say in Dirac equation, the positron has an existence only once you solve the equation for the electron, because they are holes in this infinite energy states of the electron. So there is no, so to speak, same, you don't look at the electron and positron on the same basis. You identify the positron gets existence only as the hole or the missing electron in Dirac's theory. What you call second quantization is when you put the electron and positron on an equal footing, you start out with a Lagrangian which contains terms for both, that's all, okay. And that's what quantum field theory really does. So quantum field theory has 2 aspects to it. One is that it is consistent with special relativity, which of course even Dirac equation is, but the second is this kind of putting on equal footing your particles and antiparticles, writing a Lagrangian and getting your equations of motion out of a Euler-Lagrange equation of motion using some symmetry principle to account for interactions. So we will see that. In fact, in my own course, I will set up electrodynamics for you through the Lagrangian formulation so that you can see all this on a different footing, okay. Here I just want to write down a set of Feynman rules and use that to teach you how to calculate cross sections. So we have finished the diversion, we are going back now to A mu, because as I said, beyond this, I can only wave my hands. We will see all this, or you will see all this in the field theory course where all this will be done in a very systematic fashion. So I will remove all this.
Ma'am, is there a canonical scramble approach to UFT? Like you mentioned,
No, that is the relativistic quantum mechanics, right? That is the relativistic quantum mechanics. The moment you move to quantum field theory, that's what you have. You have fields, and these fields are, you can associate a field with every space-time point in your 4-dimensional universe. Sorry?
Canonical ensemble fails in a way.
Yes, you have to account for particles getting created and destroyed, right? See, that's what I said. I just wrote down so many equations. Particles are created and destroyed. So you must have that, the number cannot be conserved. So that is why you look at it in the grand canonical ensemble. They're all related. You'll see that, as I said, unfortunately the formal structure of field theory is such that if we waited until we taught you all of quantum field theory before teaching you particle physics, which I mean in some sense can be done but is not necessary, you see, because quantum field theory deals with putting on some more secure foundational footing a lot of things that we are now waving hands at, but what we are waving hands at also has its basis in quantum mechanics itself. It's not so far-fetched. We are not getting results which are drastically different from what just pure relativistic quantum mechanics taught us. So we keep going in this direction because there's a lot to do here. So we will teach you all this stuff because we have to look at various interactions phenomenologically. Like here we are looking at electrodynamics, then we will start introducing weak and strong interactions, the Higgs mechanism. So we build up our standard model and then you can go and write down the fields for all those particles and put them on a secure footing in field theory, right? That's more the mathematical basis. So coming back to our very mundane box, A mu is equal to J mu. Okay, and now if we put this J, I have to put the Q back here again. That was the Q that we missed last time. So if you put the Q inside here and redefine, you can see then I can redefine Q J mu as the electromagnetic current, okay. Fine, and then we got the solution as A mu was minus 1 by Q squared, where Q was the momentum of the photon times J mu, and then we can call this BD or whatever, BD. So this is also BD. And if I put that back over here, then I can see that this will be, I don't know the first overall sign. So I can write it as Q J mu AC minus 1 by Q squared Q J mu. Okay, this is more or less where we stopped last time. So we can see that it's symmetric between the currents AC and BD, and we identified this term. So now we have to do some more work. I will write this diagram over here so that we remember what it looks like. A, C, because I just want to now finish this calculation over here. So what did we do at this point? We wrote down what J mu was, any of them. So let's write Fi is, so let's put the Q over here if you want, minus I Q and then we wrote phi I as Ni e to the minus e to the I Pi dot x If to the I dot x. So Q J mu, let us say AC. So we'll have NC star NA, those are those objects.
See the zero component, then there should be a minus sign
Which should have a minus sign?
in minus.
E to the minus IP dot x. You want to put it like this? Normally, yeah, normally you would have e to the minus IET, right? So you're right, it's e to the minus IP dot x, right? So the d mu phi f star, so we have a q. Well, let's not take the q right now, I mean, the q is there. We'll just put j mu. So the df star brings down, because f star will be plus I, so it will bring down plus I pf, plus I to minus I will be 1, so this will just give you pf, and d mu acting on the phi I will give you minus I into minus I is minus 1 times pi times minus 1 is plus pi mu, and then e to the minus I, so f star will get minus, so this is pi minus pf dot x. So this is, so I've dropped the q, sorry, so sorry, nc star na, nc star na pf plus pi mu, and this is e to the minus I call this, so sorry, not pi pf, sorry, this is nc pc pa pc iq dot x. Is it clear? Similarly, I can write j mu of bd, that will be nd star nb and pd plus pb mu, I need to the minus I pb minus pd dot x, and now I put everything inside here, and what do I get for TFI? So I have to put everything over here. So TFI is equal to, so let's bring that q squared outside, I don't want to worry about it now, d4x. Now this term, so let's write some more terms, n a, nb, nc star. We'll get rid of this very quickly. By the way, I hope you realize that the normalization is just 1 by square root of the volume, right? Because then this will be normalized to 2e states in a volume V. So that this is just root V, root V, root V, root V, this is just V squared. But okay, let's not worry about that for now. And then we are going to have a term which looks like PC plus PA mu, then we are going to have PD plus PB mu and a minus 1 by q square. And I've pulled it out, maybe I can even put the q squared here. Okay, then what will be left is, let us see what all is left. I have taken the n's into account, I have put this into the m, so I have an e to the minus I PA minus PC dot x coming from here. Then I have taken out the minus 1 by q squared over here, and from the other term I have taken out this nd star nb I have taken out. This PD plus PB mu I have taken out, and so I have only been left with this. And this whole thing gave me the delta function, right? So that's sorry, PB minus. Sorry, thank you. Yeah.
And delta also.
Thanks. Good. Everyone is awake. Okay. fine. I have substituted everything. I don't know the overall sign, probably made a mistake. I am going to just remove this. I think anyway I am going to square it, so it does not matter. So is it okay? So I have TFI is equal to minus IM into this. That is what I have taken out. Okay, and I minus IM is defined here, and this is simply a 1 by root V to the power of 4 and I am going to now write TFI squared. What is TFI squared? From the probability amplitude, if I square it, I get the probability of this interaction happening. So minus IM mod squared 1 by V power 4, and then you remember how I squared the delta function, right? I squared the delta function by writing, and I got volume into time. I hope everybody remembers this, and that we are still repeating what was done in the last class. And then we define WFI as the transition probability per unit volume per unit time, and therefore this Vt goes away and I get minus Im squared by V power 4 2 pi power 4 delta 4 of. Is it okay? Now what we have done is that exactly like we did it for Fermi golden rule, we have found out this transition rate, but we have some more to go. What we really want to do is to find a cross section, okay, so that we can make a meaningful comparison with experiment. So what all is left? What we have done is we have asked what is the transition rate of A with momentum PA and a B with momentum PB to go into states with momenta PC and PD. But these are scattering states, and exactly like we did for Fermi golden rule, there are so many states available for C and D, and therefore to get, we have to sum over all allowed final states, and then we remembered that in our phase space volume for C, so phase space volume for particle, let us say C, is and then I divided it out by so since it is the smallest available phase space volume, and then I drop H cross equal to 1. This gives me the number of states available for C, particle C to scatter into, but I remember that because of this definition of J mu, I have normalized to 2E states per unit volume. So for a number of particles I will have divided by 2E will be the number of states available in this volume for a certain particle, okay. Because if there are 2E states in this volume, then for the one particle I will have divided by 1 2E states, and similarly for particle D I will have the same thing with C replaced by D. So all these scattering states are available, therefore the total transition rate will therefore be multiplying this, so minus I m squared by V power 4 2 pi power 4 delta power 4 times this phase space. So V d cube Pc d cube Pd by 2 pi cubed 2Ec by 2 pi cubed 2Ed. Is it okay so far? So this is where we stopped last time, but we have not yet got to the cross section. What does it mean that we have not yet got to the cross section? We have to see how this can be actually measured in any lab. Now in a lab I cannot take one electron and one muon and collide them on each other. It's never available to you as singleton particles. What you normally have in a lab is two cases. In case 1, what you will have is that you have some target, let us say, which contains B type particles in it, and then you have a beam of A type particles falling on this target, and then when they meet each other inside this volume, they will interact. And so in the lab you will never see this. What is this? This is one A particle interacting with one B particle and scattering into any one of these allowed final states. But in the lab you will always have an entire beam of these two particles, or you can even have a beam of A type particles and a beam of B type particles. That same B will suffice, okay, and this is called okay, fine. Normally if this momentum is P, this momentum is minus P, so this is called the center of momentum frame, whereas here it is a fixed target. So what do we have to compute? In either case we have to ask what really the experiment measures is how many A and B particles in unit time, because this is WFI is the transition rate per unit volume per unit time, right. So in that volume in unit time, how many particles of the beam and target or of the beam and the other beam are actually interacting with each other to produce the final states, and only that we will be able to actually measure in the lab. We will not be able to do one on one. Okay, so what is this called? This is called the initial flux of particles. So what we have to ask is how do we compute this initial flux? So it's very simple. How many particles are, let us take this first example, case 1. Let us say that this is unit area of cross section. Now let us say that, let us take a 2D so that you know beyond this is B, and so the A is falling on the B particles. So this whatever particles are there in the beam at, let us say, t equal to 0 have just reached B and can start interacting. How many of these particles will reach this point in 1 second? Suppose I say that the velocity of these particles is VA, then in unit time all these particles which are a distance VA, because in 1 second all these particles from here to here would have reached the detector, or sorry, which would have reached the target B and started interacting with it. So we must consider all the particles that are there from here to here in this beam. How many such particles are there? I said let us take unit area of cross section and this length is VA, so the volume is VA. We know that in volume V there are 2 EA particles. So in a volume VA, small VA, there are 2 EA by capital V particles. Now these B particles are sitting at rest, so essentially all these particles can see all the B particles, which means that they will see 2 EB particles per unit volume. And this is what I call the initial flux. You can repeat the calculation for case 2. What happens in case 2? Let us say that they have just touched each other at time t equal to 0. So all the particles in the volume which is of length VA and the length VB, but you can see because they are going in opposite directions, the overlapping length will be VA plus VB, right. So that is the, let me write it here. So case 2, F will be equal to VA minus VB because they will actually add up times 2EA 2EB. Is this clear? Because they are going opposite to each other, right. So they will overlap by an amount which is essentially, is this clear? And therefore I write it as VA minus VB. And the flux is a positive definite thing, so let us write it as this.
We use relative velocity.
Yeah, V is in this direction, no? So V is in this direction. So this is a vector called, let me write it again, it's not clear. So VB is in the opposite direction, right? That's why there's a relative minus sign which will actually add because they are just in the same axis and back to back, right? So this is essentially mod VA plus mod VB, but it's there, they will be adding up together and it's the positive direction. So whether you take x axis along this side or that side, the flux is a positive definite quantity, and that's why I put a modulus on it. Is it okay? So now what I am going to do is I am going to include that also. So now I will call cross section is defined as WFI by initial flux. Okay. So why do we do this? Suppose I do my experiment, I have a very fat beam, okay, and then I have a target which is some whatever your this thing. Somebody else has a very thin beam or is doing this kind of center of momentum frame. So obviously the experimentalist 1 and the experimentalist 2 are going to see very different WFI, right. So you do not want to care about whether the experimental setup is 1 or experimental setup is 2 or even something in between. So what the theorist wants to do is define some quantity which we call the cross section, which will not worry about any of these experimental setups. So this is, if I could find one particle interacting on another particle, which is really what I want to compute, which is the heart of my calculation here, this is all I want to do, right. But since the experiment actually has to worry about so many initial states and so many kinds of setups that are possible in the initial configuration, the experiment will actually have all these difficulties. But when I write my cross section, I will write, this is the symbol for cross section, I will write it as whatever minus Im squared 2 pi to the power of 4 delta power 4, the energy momentum conservation. I will just call it as phase space, which is this portion divided by f. So I will compute a cross section and give it to the experimentalist. He will put whatever configuration he wants. From this he will extract the cross section, which will be the invariant quantity, and it is invariant in the sense that it is actually a Lorentz invariant quantity. Okay. So I want you to do two things as homework. So I will remove this. So I want you to show that the volume terms cancel and 2, show that sigma is Lorentz invariant quantity. So if you have any difficulty, you please ask on Slack. So first you can show that this quantity, so the volume elements will cancel. So by the way, now we have said that WFI was the transition rate per unit time in some arbitrary volume V. Now you can see that since it is independent of the volume, we can always say that WFI is the transition rate meaning already time is taken care of, transition rate per unit volume, because the volume does not occur at all, which is very good because I do not know how to define the volume, right. What volume do you take of the state? We have no idea, but this is true for any volume at all because the volume terms cancel out, and therefore you can call this the transition rate per unit volume. You are also therefore allowed to normalize your states as 2E particles per unit volume, because you know that volume will never occur in any of these expressions, and so you can go back and say that your rho in your J mu was normalized to 2E states per unit volume and not per some arbitrary volume V. Okay, so that is the first statement. The second statement, yeah, ask. Who?
Ma'am, I was never able to understand the meaning of true meaning of cross section in context of a schedule.
Yeah, I will come back to it. I will explain the second point and then I will come back to it. Okay. So the second point, you can show that therefore this quantity, the phase space by itself is a Lorentz invariant. The matrix element will be a Lorentz invariant, and of course your delta 4 function is a manifestly Lorentz invariant. So I want you to show that essentially you have to show that this quantity is a Lorentz invariant. So that means, let us say, show the phase space terms are Lorentz invariant, and show that flux can be written in a Lorentz invariant fashion. So for that, let me just write one example. So I will come back to your question, Weber. I want to just set up this problem, I do not want to abandon it here. So you remember the flux was 2EA, 2EB. Now I am going to drop the volume element. Let us take this VA minus VB. I can bring the EA, EB inside the brackets. So I get EA, VA, EB minus EB. Can anyone tell me what this term is? What is EA, VA? Relativistically, what is EA, VA? Anyone?
Flux, I think.
No, this is the momentum of the particle. 3 momentum of the particle. Here, okay, E is equal to m gamma. I have dropped the c squared, right? P is equal to m v gamma, that is equal to v e, right? Gamma is equal to 1 by root of 1 minus v squared by c squared, that is equal to E by m.
E is the rest of us.
E is the energy, P is the 3 momentum, m is the mass, gamma is this. Gamma is always E by m. You might be familiar with looking at gamma as E by mc squared, but for me C's are all 1. So gamma is simply E by m, which is also 1 by root of 1 minus mod v squared by c squared, and so P is mv gamma, which is v by E, right? This is just special theory of relativity, right? So this is PAEB minus PB EA, and what you should be able to do now is to write this in a Lorentz invariant fashion, and as a hint I will tell you that it is related to PA dot PB 4 momentum squared, oh, sorry, it is related to this, you can find out what it is. And remember that modulus is nothing but square root of the square, right? Mod A is equal to square root of A squared, so use that again. Okay, so will you complete this? So once you say that this is an invariant, I don't really care whether I'm in the center of momentum frame or the fixed target frame, whatever I am in, it's an invariant quantity, I can always calculate it, okay. So what I am saying now is that I have a cross section quantity which is defined. The third thing is that I show that the dimension of sigma is L squared. That is why it is called a cross section. So what you physically mean by a cross section is this. Suppose I have two beams of particles A and B and I am shining them on each other, okay. Or if I have in a fixed target, I have a beam and I am shining it on, let us say I have a torchlight and I am shining it on a wall or something like that, okay. So there is a certain area of overlap, a geometrical area of overlap, and of that some fraction of particles will interact. So this cross section is essentially that it is in some sense related to the geometrical area of overlap, except it is a dynamical quantity, so, but therefore it has so much dynamics inside it, but for that reason it still has a dimension of an area. So it is like what is the overlap area of these two beams or this beam and target, and that geometrical quantity is the cross section. And what we say over here is that suppose I say that I do an experiment and I get 10 events per day. Now somebody else does another experiment and gets say 250,000 events per day. But it is the same two particles which are interacting under the same interaction, let us say electromagnetism. Both of us are doing electron muon scattering. He gets some 10 events a day, I get some 25,000 events a day. How do I compare these two numbers? There must be inside, somewhere in the core of it, something which does not depend on the experimental setup, on how fat or thin the beam is, what kind of target I have used and so on, okay. There should be some core fundamental theoretical quantity that captures the essence of what this interaction really is. How strong is the interaction between electrons and muons when we consider that only electromagnetic interaction, that too without spin, is occurring. And that core concept is actually captured by this cross section, okay. So what you have to do is you take one guy's 120 events per day, okay, convert it into second, if one is per day and one is per year, convert it into uniform seconds, okay, and then remove, so this whatever quantity, so okay, maybe I should just write that part again, so I will take this off, now it is done. So I have a certain cross section calculated for this process, right. So what I do is that, so defined as sigma is equal to, so what I do is that I take my theoretical cross section sigma, experimentalist 1 takes his initial flux, so which he calls, the flux is usually called F or phi, does not matter, F, okay, and that may be energy dependent, it may be so many things dependent, multiply it by sigma, okay, and that gives me the number of events per second that experimentalist 1 will see. Now the experimentalist 2 will take the same theoretical sigma, he will get the number of events per second, that may be 40,000, okay. So the two numbers on the two sides will be different, but these quantities are the same. Did you understand? So this probability of interaction gives the number that interacts per unit volume, which we now forget about, per second, right. So whatever his initial flux may be, so sigma times that initial flux will give me his event rate. So the event rate in one experiment or event rate in another experiment may be different, but at the core of it there is a cross section which is the same. Does this answer your question, Weber?
Yes, ma'am.
Okay.
Now I got it.
Okay, fine. So that is why for theorists cross section is the key quantity, okay. This is what we are always going to be calculating. So now we have to come back, yeah.
Ma'am, the homework you have given.
Yes.
So for if we have to prove, just like if I have to show Lorentz invariant vacuum.
Yeah.
So we have to go through all proof or just take result and just show it.
Okay, maybe I will make it more specific. So I have given flux, I have given you the hint, right? You have to write it in terms of Pa dot Pb squared something something, okay? And you can see that once I write what is Pa dot Pb, it is Pa mu Pb mu, it is manifestly Lorentz invariant. So the other quantities that can come here can only include the masses of the particles. because mass is a Lorentz invariant quantity, it's a constant, right? It's the Lorentz invariant quantity that Einstein found, right? He said that if you have a particle with mass m, it's a geometrical quantity, it is that quantity which, if you have a 4-dimensional space time with energy on the time axis and momentum on the thing, then the invariant distance between them is E squared because it's a Minkowski space, and that is a constant by definition of the invariant, and that constant is nothing but the mass of the particle, right? So that is the original Lorentz invariant. So you can write it in terms of Pa dot Pb and some masses of the particle. That will tell you that F is explicitly or manifestly Lorentz invariant. Now here what I want you to do is, I want you to take d cube P, the 2 pi cubed is of course a constant, 2e, and I will give you a hint. You can write this as d4p by 2 pi power 4 into 2 pi delta of p squared minus m squared times theta of p naught. Okay, so I want you to show this. So you can write p squared is equal to p0 squared minus p squared. So this delta function becomes p0 squared minus p squared minus m squared. But what is p squared plus m squared? What is p squared plus m squared?
P square.
Very nice. And I can write this as, take the P0 part of the integration. Now you can complete this. Use so when you close the contour P naught from minus infinity to infinity, you can see that only one of them will be satisfied, and I put a theta function of P naught over here. So you can see that both the terms won't contribute, only one will contribute, and that will give you exactly this term on the left hand side, and this right hand side is manifestly invariant. So you can see every term is manifestly invariant, your cross section is manifestly invariant quantity. So please complete this homework like this. I don't want to spend more time on it. If you have any difficulties, send me a message on Slack, okay? So we have still not computed the cross section for this process, but before doing that I want to make, I think we will not even compute it in this class because somehow we got delayed in this class. So we will compute it in the next class, but I want to set up certain things over here now. So what are we going to set up? I am going to set up something called the Feynman rules. For scalar means no spin, right? So what do I have? If I have some particle with momentum, let's call it A and C only, or should we call it something else? Maybe I and F, interacting with a field A mu. So this vertex is mu. Then I associate a vertex factor with this vertex, which is Q times Pi Pf plus Pi. You remember that? I will put that back because I am sure you have forgotten. So now we are looking at the dynamics of things. Then we will look at the kinematics. So dynamics, we had minus Im was P A plus Pc mu minus 1 by Q squared Pb plus Pd mu, and there was a oh god, So there's a Q over here and a Q over here, and I'm going to put an I over here, I'm going to put an I over here, and then I'm going to put an I over here because I've defined this as minus I times M. Okay? Is it clear? So you can see that this quantity is what we have identified as this vertex. This is the same quantity over here that we have identified at this vertex. Now in fact, to make it even clearer, what I am going to do is, so I am going to call the AC vertex as mu, and I am going to call the BD vertex as nu, and I am going to call the propagator A mu, which goes from the point mu to the point nu. I am going to associate it with minus I G mu nu, that is called the momentum Q by Q squared. Okay. So I will, I unfortunately ran out of time, I won't be able to complete that. What I am going to do is that, have you done the Green's function technique in electrodynamics, classical electrodynamics?
Not in that detail.
So what I'll do is that,
I have read about it.
okay, so fine. I think it is a very useful thing. You will not get the same propagator. In fact, the contrast will be interesting. But the whole notion of advanced and retarded Green's functions, okay, you can compare it with the Feynman propagator. So this is also going to be related to that. So I don't have enough time to start it now. In the next class, I will simply take Green's function technique to solve problems in classical electrodynamics and show you what this propagator means over there. Just a Green's function, and you will see that it will be related to some 2-point Green's function in quantum field theory. It will come. I will check with Ravi when he is going to start that part. He is doing scalar field theory for you now. What is he doing?
Yes.
Scalar field theory, yeah. So this is scalar QED, but he would be doing without interaction. So when he comes to photons, I will ask him to, he will show you this propagator thing. So what I will show you is what you have already studied. I will show you the analogy with Green's functions in electrodynamics. I will do that in the next class. But what I want to do now is, I want to use this simply as a recipe. What is the recipe? Let us go over it. Let us write another diagram. I want to write, in fact, let me write this. I want to write electron positron annihilating to muon anti-muon. And I can write this diagram like this. You can see why immediately. Here comes an electron, here comes a positron. They annihilate into a photon, which produces a mu minus and a mu plus. Okay? Or let me take another example. Let us take an example of okay, through electromagnetic scattering. Let us take pretend that quarks have only electromagnetic interaction. Let us ask how we will write the diagram for, or even this we can write E minus E plus goes to 2 gamma. This is also an annihilation process, right? So the same thing you can have. You will have E minus E plus goes to 2 gamma. Okay. So we will ask why these diagrams and why not other diagrams in 2 minutes. But all I want to know is, how do I write the matrix element? How do I write the cross section for all these diagrams?
And the third diagram, last diagram.
This one. This one.
Yes, ma'am. What is the bold line connecting the electron and positron?
This is the electron.
Virtual electron.
Yeah. So in fact, I'm going to do all that now. So just all I want to show you is that, how will I write the cross section? I will write matrix element squared, then the phase space for this and the phase space for this, or the phase space for this and the phase space for this. Momentum wise they are the same. If I call them A, B going to C, D, the phase space will be the same for all of them, right? The initial flux I can set up so that it's the same for all of them. So the only thing that changes is the matrix element. And what do I do? At this vertex, I will write IE gamma mu. At this vertex, I will write IQ gamma nu. At this vertex, I will write IE gamma mu. At this vertex, I will write IQ gamma mu. Here, if the momentum is q, I will write the propagator here. Here, I will write this propagator here, and so on. So all I want to show is that the Feynman rules are like building blocks. I don't need to go back each time, write the TFI and derive it. Given the diagram, I can always write down the matrix element simply by inspection. Is this clear?
Ma'am,
Yeah.
ma'am,
Huh.
how do we know for any particular diagram?
Yes.
How do we know about our propagator?
Yeah. Oh, I haven't told you what is the, okay, I haven't told you the fermion propagator. So this is, this notation is, this is for the photon propagator, and this is for your electron or whatever propagator, yeah?
Right, I know you
Huh.
are.
What was your
define
question?
fermion propagator means how do you know in place of that fermion propagator
Huh.
why cannot be used?
No, I'm going to do all that now. I'm going to just wait, it's coming, okay? So first thing I want you to appreciate is that given a certain set of Feynman rules, you can always write down the matrix element. Is that clear? First point is clear. I have not yet, I will come to your question third. The second point I want to talk about is what do I mean by a virtual propagator? What do I mean by virtual? So let us take this example. Our usual E mu goes to E mu, okay, and that is this diagram over here, and let us write down the momentum q. Q is equal to Pb minus Pd, right? So q squared is equal to Pb minus Pd squared. What is Pb squared?
M square.
Very nice. So this is m squared. Pd squared is m squared minus 2 Pb dot Pd. That is mb squared plus md squared minus 2 EAED plus 2 3 vector PA PB dot PD. Now B and D can have any momentum at all, any energy at all,
Here will be a
but therefore we can see that q squared not equal to 0, right? This is a varying quantity. Can you see that?
yes, ma'am.
Not only that, let us take the massless limit. So let us forget these two masses. We know the energy of a particle is always larger than the momentum of the particle. So you can even see that q squared is not only 0, not equal to 0, but it is negative. It is a space-like vector. Is this okay up till here? So virtual means that it is not a particle, a physically observable particle which is on shell. It can only be emitted by some particle and absorbed by another particle. It cannot freely propagate as a physical particle by itself. Let us take this second example. What is Q over here? This is A and this is B. So Q is PA plus PB. So Q squared is PA plus PB whole squared, which is, let us take it to be massless so that we forget about it. It is 2 EA EB minus 2 PA dot PB, and that is greater than 0. So in a diagram like this is space-like virtual, and in the diagram like this is time-like virtual. Is this clear?
Ma'am, but the space-like virtual also you can draw it a little asymmetrically as if the Q is propagating forward.
No, I mean if you want I can draw it like this, but this is always time. This is always time. If you want I can draw it, if you prefer you can draw it like this. Okay?
The space part, E minus E plus the Q part.
How else can I draw it? I cannot draw it any other way, right?
Yes.
Okay, that's why I drew stick figures. You can see the difference between the two, right? So here the thing is like this, and here the thing is like this. That's all I want to show. I mean, if you want to decorate it by calling these angled like this, it's your choice. But basically, the vertical versus horizontal are differently virtual, but they are both virtual. So you can see that at a time, 2 of the 3 particles at a vertex can be on shell, not all 3. Okay. So this is, first of all, we have now understood why we call it a mediator of interactions. We call it a mediator of interactions because it's some virtual object being exchanged between the 2 lines. Yes, ask.
Ma'am,
Huh.
in right corner figure,
Huh.
last. No, this one. Yes.
Okay.
So in this figure, so the photon is our propagator.
Yes.
So, but it is time-like propagator,
Yes.
right?
Yes.
So
Exactly.
Can it be seen?
No. A photon can be seen only when q squared equal to 0, neither space-like nor time-like, but light-like, right? What is the equation? P squared equal to m squared, right? This is your central equation. Relativity tells you p squared, where p is the 4 vector, p squared equals to m squared. So p squared has to be 0 for the photon. But it is neither 0 here nor 0 here. Here it's less than 0, here is greater than 0, but it's not 0. It's not an observable.
Yes, it is true. But in the place of photon propagator, if in some process, if there is in the place of photon propagator in that process, in some process there is, let's say, fermion propagator.
Yes. So you can calculate the same thing here. So all I wanted to show you was this diagram and this diagram, there is no difference. Here, this is a space-like fermion propagator, right? So any particle which is being exchanged like this, which has 2 ends fixed and not free, is an internal virtual particle and is the propagator for that process. So although we started out by saying that the photon is the mediator of electrodynamic or electromagnetic interactions, the propagator can be anything. It can be fermion, it can be electron, positron, photon, any particle which is there in the theory, but the interaction will not happen unless there is a photon mediator, because at this vertex there is a photon, at this vertex there is a photon, because a photon mediates electromagnetic interaction. But the photon can be real. For example, you can now write Compton scattering, right? So you can write E gamma goes to E gamma, right? How will you write E gamma goes to E gamma? Just write it in your notebooks. And tell me when you have got it. So you have E, and then you have gamma. So how will you then, join the dots? So the main thing to understand is that photon has no charge, so photon cannot interact with itself. Photon can only interact with electron or positron. So I can have a diagram like this. E gamma goes to E gamma.
Virtual is.
Yeah, this is the virtual particle. This is looks like this, right? Is this clear? Is this clear? Now look at this diagram. This diagram. So now what did we write? So E plus E minus goes to 2 gamma, right? Suppose I had written like this, E plus E minus. How I wrote here, E plus E minus goes to mu plus mu minus, right? Suppose I had written the same way, E plus E minus, and then what could I have? I can only have a gamma here. Now how can a gamma goes to 2 gamma? A gamma cannot interact with itself. That's why this diagram was not possible, and I wrote this diagram where I wrote E plus E minus like this, and then gamma coming out of each vertex. Is this clear? Of course, I have one more diagram, and we will calculate all these things, by the way. I can have this gamma coming from here and that gamma coming from here. They are identical, so you will have to add both. You will never be able to tell whether the gamma came from the top vertex, this gamma came, or it came from the bottom vertex, right?
And the 2 gammas come from one vertex.
You tell me whether 2 gammas can come from one vertex. So we are saying that Gamma cannot interact with itself, and the only diagram. So now we come to what we have not done, because we have not done the field theory. So what this is a statement now I am making, and when you write the Lagrangian you will see that this is true. The only vertex, that is why by the way we take this as the first example in electrodynamics, whether it is spinor or scalar electrodynamics, is this. That is all. Okay, in spinor electrodynamics. Let us write very clearly spinor electrodynamics. Okay. So this diagram is there in scalar QED, but we are not going to do this because this is not easy to calculate. Okay, so we will only look at this. Scalar QED means that this particle is a scalar. We are going to soon move to this particle being a proper spinor, so we will only take this diagram with us. Okay, so at present we will only have, what is this called? This is called a 3-point vertex. This is called a 4-point vertex. So somewhere towards the middle of this course, I will actually write down the Lagrangian and show you why there are only 3-point and not 4-point vertices in the theory. But this whole thing was to show you the technology for how cross sections are calculated. Okay, so I will stop now. In the next class, yeah.
How you will do pair production type process if you want to show pair production?
Here, I wrote the diagram somewhere, no, for pair production. Here it is.
No, that is
Here.
not, I think pair in relation. I want to know pair.
No, this is pair production. No, you mean that E plus E minus production. That is the other way around.
And when are there any here are only two type of propagator?
In our theory till now there is only one fermion and one electron, right? Or other one like pseudo fermion, because we have dropped its spin. So in the next class I will complete this calculation, but then we will go on to the Dirac equation. We will go back to a particle which has both spin and charge, and then we will set up the technology for that. I just wanted to get you guys started off. So we will complete this calculation because we have little more to do. I have now talked about the dynamics of things, but we have to do a little more with the phase space. That is only kinematics. So we will do that little reduction of the phase space next class, and then we will calculate the entire matrix element and therefore the cross section. It does not tell us much, it just tells us how to calculate. From there we will go on to Dirac equation. So next week I want you guys to revise. So let me see, I have a little question mark about next week. I may not be free. So if I am not free, then I will tell you specifically what all to read up in Dirac equation, and if I am free then I will do it in the class. Okay, so I will let you know by Thursday for sure. Is this okay? Is up till here okay? So we have come to the notion of a cross section, and now we are looking at how we can just abstract away the Feynman rules and write down the matrix element just given a diagram. Okay, so we will stop here then.